Okay, so about what we will do today during the class. The first thing is we'll course the asymptotic optimality of the LP-based policy that have been sought to use n-restless bandit in finite horizon. So this will take kind of half an hour, 40 minutes, I guess. And then what we will do is we will see a more advanced bandit problem, which is called weakly coupled NDP problem. Because right now what we have seen is kind of just one constraint only on action space. Right? We see a more complex setup, and we try to we design a new kind of algorithm to solve it. Then during the lab, first I will start to a bit show you a bit, go with you through the correction of the lab of yesterday, because I guess most of you we have not been able to go through the LP. And what is important is just that you understand really well how to program the LP, because we use it, all the time. Actually. Okay. And then there is a second lab, which is about implementing this algorithm, the projection policy, for a simple problem, a toy problem. Okay, so just before I start to do the proof, I will just do some kind of recall of yesterday, so that everything is on the same page. Okay. So when I talk about n-armrestless bandits, you have to remember that we have basically n Markov chains, which are evolving independently, and they are only coupled by the action. So what does it mean? It means that your state space is in this set calligraphic at the power of n. So it's a product state. Okay. And we are in a simple setup where when the state has been observed, the decision maker is basically deciding which MDP it will activate and which MDP it will not activate. Again, you could have more refined control saying that this MDP should be activated in different manner, right? You can have different level of activation. But for the rest of, at least for this case, we just restrict ourselves to the case of two action, an active and a passive one, but just know that actually it's not changing anything for us. And you have a budget, which is an inequality constraint. And you say that you want that the number of arms is smaller than n of alpha, or more precisely, the average, the proportion of arms which are equal to 1 that are activated should be less than a certain proportion, a certain probability. So this is why we have the n and the alpha cell. Okay. We could easily put an equality there if we want. But in some sense, at some point, you will have to round the real numbers to integers and be able to satisfy an equality constraint, and it's not so easy. So actually, it's okay. For now, we just restrict to this inequality constraint. It's just making things much simpler. Once the decision maker has done his action, right, has select which arm is passive, which arm is active, it's first collecting the reward, right, generated by every action, and note that the shape of the reward is just the summation of the reward. This is also something that we'll be able to relax tomorrow, and we'll see that actually, as long as you take convex reward, you are in good shape. You are not obliged to take separable reward in every arm. And then what's happening is that every Markov chain is evolving, right, with the probability of being in state S and action A. Okay. And the objective is to maximize the expected total sum of reward over finite horizons. Also, one big thing that we have seen yesterday is because we assume that arms are exchangeable, it means that there is some symmetry there, right? So what's happening is instead of just working on this big state space, we will work on the empirical distribution of the states, right? Because actually, two arms that are in the same state, and when the same action is chosen, provide the same reward and the same function problem. So this is why we will work on, at the end, we design a policy on M. Right? So now I will just write down this on the whiteboard. Some notation to remember. Ms of t because this is a fraction of R in state S at time t. Then Ys a n of t is a fraction of arms, sorry, in state S, and so and where the action A has been selected. At time. Okay. Really good. And what we have seen is the major problem of every bandit problem lies in the budget constraint. What I put the budget constraints there? Because it's coupling random variable. And you want that the sum of random variable to be always smaller than alpha. And actually, we don't know that, right? And the classical way of basically solving this problem is take the expectation. This is making the problem much easier. And then find a way to interpolate in the sense that solve the problem in expectation and find a way to go back to the n-arm problem where actually this constraint is set. So this is the entire kind of trick that we are trying to do. Okay. So this is the LP, but this I will write it down again. And what you have to realize is first the following, is that we have defined a set of feasible controls, which are basically telling us the following. Imagine that I'm giving you a distribution of the state. So basically, I'm giving you MSL of T. Find a way to split them between two actions. So this is the way you split, right? Such that you don't lose mass. And such that your budget constraint is respected. So we hear it's an inequality extension like that. Okay. So note that the way you split is it's real numbers. It's not integer yet, right? But at least I'm giving you a probability basically, given a proportion of arms in state S, assuming that, let's say, 10% of my arms in state S, how should I split this 10% between two actions? Perhaps I can take 1%, I will activate them, and 90%, I will not activate them. But then we will have to go through the integer, right? Because actually our program is about, we have finite arms, so we have to decide an exact number, right? Percentage or not. And the way to do that will be to do around it. So let's go back again to see the projection policy. How does it work? And this is what you will have to program today. Actually, the lab is really quick because you just have, and I've just described the different steps. The first thing is you have to solve your LP. The second thing is you start your initial state. You compute your projection, and basically for every empirical distribution, right? So when I say an empirical distribution, I hope that everyone understands that, perhaps the easier way to understand what is an empirical distribution is when you have some data and you do a histogram. This is what we call an empirical distribution. So you give an empirical description, and it's giving you a splitting of action per state, the proportion of active arms per state, right? Which is as close as possible to the optimum LT. Okay. Then you have the rounding step, right? Where basically you make things integer. And then do you have any idea how do you use YN? So basically here, still not integer. One easy way is you multiply. So let's say that, for example, you multiply, what's happening if you multiply YSA by N? Can someone tell me? If you multiply YSA by N, you get an integer, right? Then it's telling you the number of arms in state S that you have to activate. So you will just have to do some kind of 2 for loops, activate N arms in state S, N, this number, and multiply by Y hat with a floor bracket in state S, and then the rest put them at 0. So this is your pulse. Once you do that, you know, like in your code, you just use your kind of simulation function to generate the next steps, and so on and so on.
So this is like a deterministic policy.
Yeah. Yeah. Why it's deterministic? Do you have an idea?
You mean why is it sufficient to have deterministic? Yeah.
No, right now we are not talking about sufficient. Sufficient. I'm just telling you why we need why deterministic is helping.
Because if you want to sample from the action state, you have to sample over much larger. You have to sample over.
No, it's much easier than that. When it's deterministic, it's really easy to satisfy these constraints, right? Just have to count a bit smartly, and you satisfy. You know, if it was random, you can always have a probability actually go outside this constraint because you want this constraint. At the end, for N arms, you're obliged to go with some kind of deterministic policy, right? Otherwise, it's just hard. Means that I don't even know how to do it, to be honest.
So you have to keep sampling till you find that constraint satisfied, and then.
No, but the mass probability at this event is really low, right? You could try to explore all the possibility with all the type of distribution, getting that, because you have to understand, it's not even almost sure what you want. You want that it's happening all the time. It's completely, it's a deterministic constraint. And you have seen that in your budget, it's actually a deterministic constraint. You have a resource, and you cannot spend more than your resource. So there is no way that you can violate this constraint. Okay, yeah.
In that previous slide, there was N inverse function.
Yeah.
N is an integer vector.
Yeah.
Like,
it's a number of arms. So please, for the people that are at the, not at the bottom of the room, but at the back of the class. Thank you. Bottom is not exactly the right word. Speak really loudly. Otherwise, I'm not understanding. I don't know why, but the sound in this room is a bit weird. I know that sometimes you cannot listen to me, so okay. So, and just now to finish is, and this is try to recall this this part, is you have an empirical distribution. You project to do the splitting. Then you have the rounding step, and then you generate your probability transition. Okay. And now what we'll prove today is that when n goes to infinity, you converge to the optimal policy. Okay. Okay.
So V relative and VLP, they're not the same quantity.
They are the same.
Huh?
They are the same.
They're same.
Yeah. LP and forget the N here. That's the same. The difference between the two is here I've taken the relaxation for any type of policy which is admissible, but not the optimal one. And when I take the optimal one, so basically when I put a minimum of a pi, then I'm getting the L. So here is, let's just apply any type of admissible policy on the LP problem. How can I so because from the survey I understood that I'm going too fast. Please stop me at any point of time if you don't understand the step in the proof. Okay. And Parimal, you will be the one that you can stop me. Okay. Okay. So now, the first thing that you have to realize is the following. I will write that. I want to understand. So for now, I will just do the proof for fixed policy, which is admissible. Fixed policy means that it's not the optimal one, it's not the solution of the end. But admissible in the sense that it's matching with the empirical distribution. It's a policy where I'm giving an empirical distribution and it's giving me a splitting, which is respecting the budget constraints. Okay. So let's call B, P, N the optimal value when I start with an empirical distribution of the initial state at N0 and by borders. Okay. Which is equal to expectation of the summation of T, summation of S and A of my reward and YSA and of right. So this is my value for finite bandwidth in the sense that you have n arms. This is my reward when I apply a policy phi. And so what I will just do is I will add a small phi. So sometimes I will forget it, but just remember that for now, I'm always using a policy phi. So I will define phi, which is basically a mapping. I'm taking a distribution, an empirical distribution M, and I'm giving a vector 1. So this is my policy. And it is admissible. Okay. Those things that you can notice is just right. Just by using the linearity of expectation. Obtaining that. Okay, we can. Good.
So why are we not considering the terminal reward of this?
Say again.
Why are we not considering the terminal cost or reward?
Because I didn't define it.
So you are considering it to be good.
Yeah. But all these things actually, it's okay. It means that you want the terminal cost to get at it.
Yeah.
There is no problem with that. There is no As long as it's linear, you don't have any problem. And in some sense, you know, you have the terminal cosine t minus 1, right? You can call it your terminal cosine, because after t minus 1, you don't do it. So if you want to have something like you said, you could do everything that I'm doing by adding a t here. By making basically your reward time dependent. And then you put all your reward at 0 until t minus 1, and we will have a terminal cosine. So if you want, you can make the reward time dependent. Everything will follow. It's just that it's an extra index that I confront with to deal with when I do the code. But I think in the original papers I've done that. Anyway, it will go. Okay. So now we will look at okay. So this is so now what I would like to understand is what is the dynamic of what's happening inside the LP, so what's happening in a bridge, right? And what is happening in a bridge is that ys of t plus 1 is equal to p m, so is equal to p of m of t plus 1. Right? So I'm taking an empirical distribution at t plus 1 and I'm getting 1. And then what's happening at m of t plus 1? It's nothing more than p of y of t, where basically, which can be written in a simpler form. So if you take p is a vector, right? And if you take p of s of y of t, it's equal to the summation of s prime and a of y s prime a of t probability to go to s prime s in a, right? So in other words, what I just wrote is that ns equal to 1 is equal to summation of s a y a of t probability for all t and for all t. Okay? So this is what's happening in a bridge, right? When you don't have any randomness, this is what's happening inside the LP. So now, remember the function, what is the cost function of the LP? What is the value function for given policy pi? What I will do is I will add small pi everywhere. Just recall that all this is basically parameterized by the function pi. Okay. So then what is the value function of the relaxed problem when I take everything that in expectation under pi and 0? Okay. Because everything is deterministic, actually. You can just take directly the Wi-Fi from there and just write your first. Okay. So the LP, when you look at it, what you have to understand is we are just solving an optimal control problem, but on a determinant, which is deterministic. This is a LP because we put everything in expectation. At the end, it can be seen just as an optimal control problem, which is determined. So this is why I don't have expectation. And basically, the dynamic of my system is described by these two equations. For the people that are familiar with optimal. So it's discrete time optimal control. Okay. Okay. What we are interested in.
So we should ask.
Yeah, tell me.
People this highest from the system.
This.
I but just make sure they remember this.
So do you understand where this is coming from. Do you not understand? Yes or no? You have to say the word because we are done. Okay, really good. So it's a no. Okay. Interesting. So I will do one remark first, because I want to conclude what I was saying, and then I will switch to what is this phi and pi. Pi, you were simply saying phi, no? Phi, I think, is not clear. Pi is a policy.
Yeah, pi is defined.
It's defined. Pi is not clear, but I will define what it is.
I mean, it's clear from last class, if you remember this. Maybe you don't want to spend too much on this.
I will do it. So the first thing is, what you have to understand is we are interested in understanding, in bounding, interesting to bound that and to observe what's happening when n is going to 0, right? And just by the triangular inequality, what we just obtained is that the only thing that really matters is to be able to bound the difference between y and I can even make it simpler. You know, it's marked with your constant and so on. This you can say that it's upper bounded by t of y and let's say summation of the t equals 0 to t minus 1 of y t minus y. Right, just by the linearity, because we have a sum. And then I just took the max of all the constant, just get this inequality. So you see that basically our main focus to prove the convergence is to prove that y, the deterministic y, is converging to, the stochastic y, when I use a given policy, is converging to y of t. So this is the only thing that we have. So now I will explain perhaps a bit more what is this phi and why we are looking at this, right? So just note that it's LP, it's coming from the LP, but now I will explain where it's coming. So what is the expectation of the fraction of arm in state S at time t plus 1, knowing yn. So basically knowing my action at time t. This is nothing more than this we have done 10 times the calculation yesterday. When you take an expectation, you take this formula. And actually, you can see that it's equivalent to say that expectation on the entire vector of the empirical distribution equal to phi of y and okay. So basically, this phi is basically what is happening when I'm taking everything in expectation. Okay.
What is the opt in that first equation.
What is
What do you mean by opt in the first equation in the theorem? In the theorem that we have on the slide.
On the
slide. What is opt there?
optimal when you use the optimal policy?
So we need that in the first equation also.
Why?
Like because it's for a fixed policy, right?
No.
The first equation. First
Just remove here.
it's not
Remove here. Okay. One second. Tac, tac, tac. C'est pas mal. Yeah.
Sir, in that, y minus yt. The last equation in the
Yeah.
So what is yt?
So let's do like this a proof. And what I will do is I will add some extra assumption along the proof just to make it simpler, and I will tell you what we can refine there and so on. My goal is just to teach you kind of the main trick, and then, you know, the rest of the assumptions that I will add are actually extremely easy to relax. It's just a bit more complicated mathematics. Okay. So as I said, we want to look at this stuff, right? So we will do a recurrence assumption. And what is our induction assumption? Is that the induction step is that at time, no, actually, we cannot do like that. We can make it much more easy. So, okay, let's look at this term. Yn of pi of t minus 1 pi. So when I look, it's perfect. I've not seen that out of my slides. It's perfect. Yeah, perfect. This is Yn, right? And we want to go back to n star, please. But remember that there is two aspects. There is the projection step, and there is the rounding step. Okay. So what's happening there? So here, just by using triangular inequality, what I can just say is it's equal to Yn pi of t. So when I call pi, I'm not always talking about the projection. It can be any type of policy which is admissible. Pi of t minus, how did I call it? Y star. So basically it's pi of n of t. So basically I'm adding and subtracting the steps before the rounding. Plus pi. So someone has an idea of this order of this term when n goes to infinity. So basically, you have to imagine that this is just a rounded version of this. That's it. So let's just look at a simple example, right? Assuming that you have nx divided by n minus x. Basically, this is what's happening. Okay. This you can always upper bound it by what? N minus 1. X and minus X. Right? I just went here. So basically, you have a point here. So rounding is sending you there. And I'm saying just put -1 and I send it here. So automatically the distance is getting bigger, right? And then, so this is basically equal to 1 over. Okay. So this term, so this term can be bounded by some constant multiplied by 1 over. Basically, the dimension of the states multiplied by the R divided by 1. Okay. So this gets bounded by the constant divided by 1. Really good. What about this term? If I naively look at the definition of y I of t, I see it's equal to pi m of t plus 1. Okay. I can just write it down. So this is where I make an assumption that not always the case. Usually what you have to assume, and the only thing that you can ensure all the time, is that pi is continuous. Okay. Usually this is what you can assume. You can assume because when you use an LP program, actually getting more than continuity is a bit more tricky. You can get differentiability. This is an interesting result that I will talk about perhaps later. But basically, you can get differentiability in a small ball around your optimum, but hoping more than that is completely unrealistic. However, to simplify the proof, I would just say that pi is Lipschitz. So what does it mean to be Lipschitz? Being Lipschitz. What does it mean for a function? Is f of x minus fy of x is smaller than k of x. So usually to do that, to have this assumption, one easy way is to say that the function is differentiable and the gradient is bounded. So let's assume that it's Lipschitz. Then what you get is you get a constant multiplied by n of t. Okay. So what we are saying is if the empirical distribution is converging to the distribution we average, right? Then we are done, right? Because this is bounded by 1 over n, it's converging to 0. And if this is true, it's also converging. And actually, by design, we know that this is converging to n, right? It's just a law of Larsen. Right? But I will still show you how. But just to tell you, by design, it is here, it has been designed that way. Now we will just work with this step. So the first thing to notice is the following. NP of NT is equal to what? Is equal to I of YT plus NP and minus P pi. What is phi? It is the conditional expectation. Where is it? It's there. It is the conditional expectation of M with respect to 1. So basically, what I'm doing is what this is in stochastic process. It starts with what we call the drift. T-1. So for people that are not aware with this concept, when you study the evolution of a stochastic process, what's happening? At every point of time, you have a random direction, right? You can go there, you can go there. Basically, you have small movement, right, of the particles. And there, you can go there, you can go there. And the drift, depending whether or not you're in discrete time or continuous time, but in some sense, is related to the average direction. In average, where do you go? So in average, for example, you will go just there. And perhaps you will just go there and so on. So you build the stochastic. And when people want to study the property of stochastic process and where it's converging, usually what they do is they look at the average equation. So basically the equation with the drift, right? Check where in average it's going. And then what you hope is that you're able to bound the error such that you are never too far from the average. So for example, people that do gradient descent and stochastic approximation, all these are based on this idea that look in the average and then you just have to manage the error. Okay. Really good. So this, I will call it E and pi of t plus 1. Basically, this is the error between the stochastic process, right? And it's E. This is the error related to that. Sorry, I was thinking t plus 1. Really good. So when I rewrite this now, what I will do is I will just add, I can just upper bound that P pi of y of t minus y, sorry, there is an n. Y n pi minus P pi of y of t, right? Plus 0.
In the second equation, no n is square.
One second. Let me introduce one second and then I will tell me.
The second equation, n is not equal, right? In the y function. And it's expected y of y by t minus 1.
No, it's exactly equal because I just subtract here. You see? I just took this. I add the expectation, I subtract the expectation. So it's equal.
Okay, I thought you were adding y pi of t.
I'm not sure to understand what is the problem.
I'm not sure whether that's superscript anymore.
Okay, so perhaps in the notation. So this is the expectation, right? We agree that this is the expectation. Plus, no, there is no point. No, but the only thing that I've said is you have a random variable Z. And I just say that Z is equal to expectation of Z plus Z, and use expectation of Z.
I think the easy way to see this is if you go to the second equation on the board, right? P of yn of t leads to small mn of t plus 1. Yeah. And you can replace yn by this regular without bn, and you'll get regular. That's what is easy. So it's writing mn of pi of t, and you're writing it by this mean, which is small m pi of n of t. Right? That's will be c by of n, and then it's the error term. So mean plus the actual random variable minus the mean.
Okay. May I erase this second line? Is it good for everyone? Oh,
Keep it.
no, but oh, it's okay. So now what we are interested in.
But I think P does not also specify the way of the
Yes, true. By safety, I put by everywhere. Whatever. So now we will look at P of yn of t minus P of y of t plus the expectation, plus sorry, the error.
So I think that's P minus 1 and both of those.
1 second, yeah. I'm sorry, I'm writing with plus 1 because I remember. Okay. Okay, so phi is the linear mapping, right? When you look at the shape of phi per component, you see that it's just y multiplied by matrix. It's even a stochastic matrix. But so what does it mean? It means this can basically be bounded by a constant, in this case, which will be equal to 1, and y pi of n t minus 1 minus p of y plus 1. Plus my error. So this error now we call it epsilon n of t minus 1 plus epsilon n of t. And again, good news. You see that if at t minus 1, this is decreasing, this is converging, we are nearly done because we have proved it before. That means that we have the intuition that if this is working, it's converging, then we are done. We just have to undo this step. So if I have to summarize the equation, right, what do I have? I have yn by t minus y of t, which is smaller than t divided by n plus I have a constant, right? Yeah, a constant. K multiplied by c of y phi n t minus 1 minus y minus 1 plus k my error. Okay. And I can even just write it down as if I call that z of t smaller to equal z plus k z of t minus 1 plus k multiplied by epsilon of t minus 1. Okay. And what you see is, imagine that I'm able to show in some sense that this is going to 0 when n is going to infinity. This is going to 0 when n goes to infinity. And just by an induction argument, you can say, let's assume that z of t minus 1 is going to 0. Then it means that z of t is also going to 0. So, but let's see how it handles the noise. Everything down. Okay. So let's look at the expectation of MSN of t minus the expectation of MSN of t, knowing y and of t. So basically, I'm trying to look at the variance. Some sense. Moment of order. Okay. So why I'm looking at this term? Basically, I'm looking at bounding. How did I call it before? Yeah, I'm looking at bounding right now. This is the norm square, right? And why I'm looking to do that, I'm looking at doing that because actually I'm interested in actually what you can prove is that first I have simple Cauchy-Schwarz inequality that the norm of x smaller than the dimension of x. So let's say that it's s s multiplied by, there is a square root, the norm of x squared. The norm of x. So this is coming from Cauchy-Schwarz inequality, right? So the Cauchy-Schwarz inequality is just saying that takes the scalar products between two vectors and it's smaller than the product of the norm. Right? And if I'm able to basically bound that, what you can do is you can just take the square root. So sorry, there is a s. You can take the square root. There is you take this, and then basically what you will be able to do is have a bound on the norm 1 of this element. And this is what we are looking for. If we want to show convergence probability. So this is why we are studying this. So the first thing that you have to note, can someone recall me the formula of the variance? Variance of x is equal to of s of what? Of x squared. Really good. So these things you have to know by heart. So what is the expectation of this term? Which is the error term. What is the expectation of this? So this is epsilon I of n. What is the expectation of that? It is just a random variable subtract by its mean. So the expectation is 0. What does it mean? It means that basically this term is simply equal to the variance of NSM knowing y and okay. Okay. So now I just recall you the definition of SNN of T. Just 1 over n. One way to see it, write it like that. So this is what you have done during the lab activity. So make from I equal to 0 to n. So basically, you activate n of the arcs, and the way you do it, you just draw a uniform random variable in 0, 1, where ui is smaller than p of s prime there, s prime a prime s. So basically, this is kind of an exercise that I'm giving you, but it's kind of easy to see that MSN of T, we have seen that it's indicator which arm we activate, we don't activate. Right? And you can just see, you can write it like that as an indicator of a summation of basically uniform random variable with this function. This is actually, you have done something pretty similar where you is drawn from a uniform function. So, what is the good news of that? This is extremely easy to compute the variance, right? Because what we are doing is we are computing the variance of ax plus ay. It's simply equal to a squared if x plus b of x. So, and the variance of the Bernoulli, the variance of the Bernoulli is just p multiplied, let's say that p is the probability of passing a coin thing. 1 minus p is to get f. Then the variance is p multiplied by 1 minus p. So if I just look at the variance of this, so let me call this equal to a. A is equal to 1 over n squared. Summation from s prime a of n y s prime a n p s prime s a multiplied by 1 minus p s prime s, which can be not that, remember that y s prime a is a proportion, right? It's a probability. So I can just talk about this by 1 over n summation of s prime and a of p s prime a and a, it's basically p prime. Okay. And from this, what can we conclude? We can conclude that from the last hypothesis. We can conclude that the expectation, you will have to use Cauchy Schwarz on this one. It's of the expectation by noise. So basically, what's happening means that here, everywhere I'm taking the norm 1. Right? So the expectation of epsilon a of t Okay, one other remark, I'm sorry, is you have to notice that this bound is universal, in the sense that even if I'm conditioned by y and of t, actually it's not depending on y and t, right? So it means that you can directly upper bound all these terms by y, 1a of t, and you have that any bound. Okay. Upper bounded by one of the okay. So remember that our objective is to study this. So let's write expectation of z of t, knowing y n of t minus 1. We take expectation everywhere. Right? And what do we obtain? C divided by n plus k multiplied by z of t. Because if you know y n, you know z of t. Well, if you know y t minus 1, you know z t minus 1. Plus k multiplied by c prime square root. I can now even, because everything is in there, take the expectation on the entire trajectory. Right? And I will obtain the for instance, c over n plus a of t minus 1 plus k prime. And clearly, you see that by induction, you can prove that the expectation is converging to z. Okay. And you prove that by induction is converging by 0. You have a convergence in norm 1, and therefore you have a convergence in probability. So the last argument is induction step. Induction plus convergence in norm 1 imply convergence in probability. So perhaps you have not understand all the steps of the proof. Means that you have understand all the steps of the proof, but you don't know how to make it yourself. The only thing that I've done is I've just taken this and I've decomposed my error at every time. And I've tried to bound it by something which is decreasing. And what you see there is actually there is only the only stochasticity is coming from the fact that I'm comparing my m hat, which is the realization of my empirical calculation, with its average. This is the only thing that I have done, because I was comparing myself with the mean trajectory. And then the rest is just some tricks about rounding and things like that. So this proof actually is quite standard. There is nothing new about this proof, nothing fancy. Everyone that has done stochastic approximation, for example, or gradient descent, stochastic gradient descent algorithm, I've seen this type of proof all the time. It's kind of the standard. You basically make a pure deterministic term. You know that with the deterministic term, you are able to prove the convergence. And then the only thing is, what can we say about the variance? And we say that the variance is going to 0. Okay. The story is not over, but no. Okay, I will now perhaps go back to my slides. So, what we have proved is the following. You take a policy which is Lipschitz, so basically continuously Lipschitz. And what we have proved is that asymptotically, your empirical MDP with n arms will converge to the true MDP. However, we have not proved the optimality. Why so? What is missing? Really good. And how do we do that? It's a really good point. So the things that you have to understand is, did you see at any point of time that I use the fact that, what did I use basically in my proof? I just say that there were a mapping between M and to the state. So basically the only thing that I've said is basically I have these constraints, right? And I've also said these constraints basically you never saw happening in my proof. But what you have to realize is if you enforce that your policy is in this set and you use a rounding, right? Then whatever type of policies that you are using, type there, whatever type of policy, it means that your policy is admissible for the n-arm problem. So what does it mean? It means the following. It says that pi is admissible, and you use this process, right? Pi is admissible. And basically, I call it y hat. If you use y hats, which is depending on n, so y hat is after rounding. What do you have? Is you have p and pi on n0t is greater with 1 than b of opt, the optimal solution of n0. You have this inequality. Why you have this inequality? Actually, because imagine that pi was not admissible. It means that pi was belonging to a much bigger set, right? Than where you optimize in the opt. Then there would be a chance that you are smaller than this, right? Because you could optimize in a bigger set, so you can go deeper in your minimization. Right? So admissible is ensuring you this inequality. Okay. What we have also seen is that we relax or VLP is smaller than this, right? What we have seen is if we solve the LP problem and take the constraint in expectation, it means that we're optimizing on a bigger set. And therefore, automatically the minimum is big. Now, let's say that pi is also LP compatible. What does it mean? It means that when it's here. It means that when you give as an input to your policy the solution of the LP program, then as an input, you should get the Y, which is the solution of your limit equation. So what does it mean? It means that what we have seen is for a given P, what we have seen so far is for a given P, Pn is converging to P relax, right? True. Moreover, we say that if pi is compatible, then B and pi will converge. B and pi will converge to B relax optimal, right? The VLP, right? You will have the convergence. And therefore, what does it mean? It means that your V opt is between two things that converge together. And therefore, V opt will converge to B relax. That's That's the argument. And you see that the two crucial things that cannot escape when you design a policy is admissibility. Admissibility is basically allowing you to do this step. Right? So this is admissibility. And then you want to say that P is converging to this, right? And to do that, you need LP compatibility. Then the way you find the policy, I don't care. As long as it's satisfying these two things, then it's good. Okay. And the projection, when I define the projection operator, is actually satisfying these two things. The only thing that is not satisfying is the Lipschitz continuity assumptions that I use to make the proof simpler, but it's not changing anything to prove them. Okay. So I think we all need to digest for 5 minutes everything, so I did a small break. And then we can switch to the other.
I'll meet at 10:25 before.
No, but slowly.
Refresh this amount.
Okay. What's it called? Okay. So now the question is more why we have done all that in some sense for a toy problem. I think most of you said when I was looking at the survey, what I think is that a lot of you want to study really complex resource allocation problem, and I'm sure that you will tell me, but okay, I will not be able to fit what I've seen there my problem because that's not feasible, right? And yes, it's really nice, and you have designed an algorithm, and you have proved that it's asymptotically optimal, and so on. However, yes, it's really nice, but still not you cannot use it, right? And actually, there is a natural extension of stressless bandit, which is called weakly coupled Markov decision process that most likely will do the trick for your process. It's like kind of a first step to study more realistic So this problem is actually coming from discussions that I have with one of my students. We've also related to optical networks and a discussion with Parimal also, is how do you do you have a set of queues? How do you do load balancing and controlling the same service rate of your queues at the same time? What does it mean to control the service rate in some sense that imagine that you have a worker that's processing some machine learning data. If it more GPU, you can always allocate more GPU, with all the network virtualization function, right? Where should I send the data? Things like that. So this is more realistic, and in data center network, it's called also auto-scaling, and this is what we see. So the scenario is the following: you have n queues that are processing jobs, and the rate of each queue can be controlled. The service rate, sorry, of each queue can be controlled. And also, the scheduler can also decide where the job should be sent. A big question that actually, no, okay. And the goal is to minimize the total load on the system. And therefore, we have two decisions at every time instant. And I didn't find time, but at every time instant, where should I send my job? And should I increase or decrease the service rate of something, right? So one thing that you have to understand in queuing theory, and especially when you want to model such continuous system, it's not like right now I always say I'm talking about discrete time, but most of the time we're working in the continuous time, right? And when you drive a car, actually it's really continuous time. But when you do scheduling, it's what we call programmation based on events, right? There is an event, for example, the queue has left, a new packet is arriving, then I'm doing an action. It's not at all the. But the problem is how to predict when an event is fixed. And this is an idea, means that this is something that we have discussed a lot with Parima about it. Is let's assume that we cannot control the process at each time instant, but we can only control the process when there is an arrival, right? And in some sense, you can see that it makes sense for the packet arrival. The packet is arriving, this is the moment you decide. But then we also say that this is the decision time for when you do the service, right? With another colleague, Ishwa, who is in the room, we have modified this model and saying that there is another clock telling us when we can do the service, right? But decision, you have to understand when you model this system, you really have to think, when do I control? Which is actually already a big question. Why? Because it will induce what do you observe? And this is why it's actually hard. When you control at every time instant, you observe everything. But when you control between, for example, two arrivals, what's happening is a lot of things can happen into the system between two arrivals. And you have to take this into account. Okay. So the arrival process in my queue is simply, I use a simple model where I assume that I have a batch of jobs that I will call alpha n, that arrive in the system with a probability P. And that Tn is the arrival time of the nth batch job. So you have an arrival. So the time is discrete, it's logic, right? And at every time instant it does come. If it's with probability P, if it's head, then you have alpha n new jobs at that point. And with a probability 1 minus P, nothing is happening in this time step. It means that no new arrival in this time step. And because we are just tossing a coin, the arrival process is independent and ID between arrivals. So the only thing that we have to do is kind of the time, we are interested in the time between two arrivals. It's called the inter-arrival time. And it's just following a geometric distribution. Okay, right? So basically, 1 minus P is the probability that no new arrival is coming. So the probability that there is T time interval before any new arrival is equal to what? To the probability that during T minus, tau minus 1, nothing is happening. And then at tau plus T, right? Something is happening, so it's with probability. So let's look at the dynamic of the queue. So as I said, and this is actually the tricky part, your queue is only observed at the arrival time. So the length of the queue, which is the QK, which is denoted by S, at the n plus 1 arrival, at the n plus 1 arrival of, at the n plus 1 batch arrival of jobs, it's equal to what? The length of the queue at the previous arrival minus all the departure that have happened during this interval. Because it's independent, you can just look at the interval between the two departures. Plus the ones that have said at time T. Okay. The ones that have said at time T. K is the finite buffer size. So I'm always studying finite queues because just when we study rapid bandit, having a finite space just makes the math easier.
You need actually K minus alpha.
K minus. Yeah, absolutely. So you need to add a plus AK here. Yeah, a plus n. No, it's 1. You just take 1.
Okay, because you said
you have n alpha, but I didn't say how to allocate n. So when I allocate my n alpha job, I only
take 1.
Give 1. Of course, it can be extended to more complex batch size. The theory will follow, but it's just like that. Okay. So DK is just the number of process jobs, right? And what we assume is that the probability that the job is processed at time t can have two values which can be controlled, which is kind of a low processing rate and a high processing rate. But what we will assume is that the processing rate is constant on an interval, right? You cannot change. And the AK of t is equal to 1 if you send one job, and otherwise to qk, and otherwise it's equal to 2. And again, it's not really a problem if we want to send 10 jobs. So we can do the thing. Okay. So one thing that you can
this the part of it I didn't understand. So
it's departing at a rate pk of t. And between two arrivals, because we are not changing, it's just pk of t minus t minus 1 minus.
So it's so pk is a constant.
It's a value. It's like a job is processed with probability.
Yes. So that it doesn't have to be constant. Right? It's a Bernoulli
It's a value.
It's a binomial.
Yeah.
It's binomial.
Exactly.
It will be random.
Yeah. Okay. So this equation looks a bit complex, but at the end, because we're only looking at events, what you see there is we don't need to really take care of the time. So real time, we only need to know the event and interval of arrival time, right? So the things that we can just rewrite this equation as follows, right? Where the length of the queue at t plus 1 is equal to the length of the queue at t minus the departure time if between the two arrival time they were is of size 2. So basically, if the arrival time is of size 2, then you have a certain amount of departure during this interval, plus what you have. Okay. And you can just do the maths. I will not prove it there. I was planning to prove it, but not now, because we have other things to talk about. But basically, you can prove that the probability that you go from S to S prime, knowing whether or not you are accepting a job and knowing the departure rate, is following this law, which is just a combination of the binomial law and the geometric, right? So no, perhaps I will still do a part of the proof such that you understand it. So, what is the probability of departure between tk plus 1 minus tk, which is equal to, let's say, to departure d, knowing that S of tk is equal to S A of tk is equal to A, and tk plus 1 minus tk is equal to so this is just, we have seen it yesterday. This is nothing more than a value where I just need to give the conditions that the possible event, right? So it's kind of the support of my distribution. Because I can only use, one job in every time interval, right? At maximum, I can lose 2 jobs, bigger arrival times. And also at maximum, I can process only the jobs that are there, which is S plus A. So S prime, you cannot process more than this one, right? So I hope that it's clear. And then you just, so let's, then you just put it in the binomial, right? So it's S prime, minimum S plus A. So my service rate, which I call it B, So we call it B of k plus 1 minus k at the power of s prime. 1 minus b of k plus 1 at the power in, oh, I will call this, I don't know, C, C of 2 S A. Just to make I like to. C of 2 S A minus S1. So then what's happening? Yeah.
It will be the number of jobs, but tau is in time.
Yeah. But tau is discrete time. So you have intervals and you just process one job at a time in the given time. Really good. So now what we are really looking for is the probability.
So just one doubt there. So you're using this PK plus 1, but your slide is say P plus 1. So
yeah, because I just replaced by event.
You are assuming that
it's N if you really want.
PK is your P.
Right.
Okay.
So the probability of k plus 1 and k is equal to E. Knowing this time we want to arrive the arrival time. S knowing S of k S and A of k is equal to what? To the summation of tau equal to 0 to plus infinity. No, it is mean of S plus A of the probability that k plus 1 and k is equal to 2 multiplied by the probability that E of k and k equal to knowing S of k is A of k of A and k plus 1 times k equal to, right? So basically, I'm trying to understand what is the probability to have a certain departure for any when actually I don't know the arrival time, right? I don't know yet. And this is nothing more than the geometrical. And this is basically how you get this. And why you are obliged to say that it's the summation is only going up to S plus A, because after that, your Q is empty, right? So you cannot have more data, even if it's the right weight. So basically, okay. Okay, so now we have our complex transition matrix. Let's talk about cost function and constraints. What we have is we have what we call an energy cost, which is depending basically of the length of every Q, and also on whether or not I'm using a high service rate or a low service rate, right? So what is really nice in this problem is you can see that in some sense we are starting to grow the symmetry of the problem, right? Because now we can have Qs with different service rates. Okay. And we also have a cost which is related to job rejection. We don't like to not accept the job, right? It's not good, right? Because we say to customer, I know you cannot enter, Q is empty. I think all of you, that happen when you go to a restaurant and someone is saying it's full. sometimes if it's happening too often, you are like, I will never go there, even if it's not that old that old, right? So this is a rejection. And then you have the constraint saying that you cannot allocate more than the jobs that you receive at every time instant. And you cannot, you have also an extra constraint. You cannot change all the sample strings. You just can change some of them, right? Because it's costing, it's costing deployment costs and things like that. So there is a difference between this constraint and this cost. This cost is saying that having a high service rate means that I'm consuming energy, right? And this cost can be seen more as a deployment cost, that I have a finite number of, for example, GPUs that are there that I can allocate it to some workers and I cannot allocate to others. And you see that this problem is much more complex than the ones that we have seen because actually we start to have two constraints, right? And this can be handled using weekly components. So I've just taken back the slides that I've used yesterday and just modified everywhere and restless landed by weekly component, just to really understand. So don't be surprised that you have the same format. So what is a weekly component? It's again, you have k arms, which are the same transition matrix, and that have the same state space. And you have action, which are belonging to set A, but this time action is not 0, 1. It can be multiple actions. So in our case, what is an action column? These are examples that I gave. It can be admin or not admit the job, right? And high service rate, low service rate, and not admit. High service rate, not admit. Low service rate. So you have 4 actions. And we assume that the decision maker has to respect the following resource allocation constraints. So basically, the constraints are now depending on the state of the harm K and also on the harm. So in the previous example, it's only depending on the actions, but because it did not come naturally to the constraint on the state. But for example, when you look at the deadline scheduling problem, because your state is of size 2, most likely you can formulate with this type of. So how does it work? Again, like in a restless bandit, you first observe the state. Then you take an action based on the state. You take an action A such that this is set. And actually, I'm saying something extremely important. Means you have to understand the ordering. You take an action. So now some of you have done stochastic programming. No? Okay. So usually when we do stochastic programming, what we try to do is to find a control such that with high probability, the constraint is set. But because we observe the state, right, we don't need to put a constraint in high probability. We already know the state. And then we can just adapt our actions such that this is set, right? And this is a really important point. You have to, otherwise you will not be able to guarantee these constraints. So you have to remember that you take the action after observing the state. And sometimes it's reversed, right? You could imagine a scenario where you take the action and then you have a constraint on the next state. And then this is problematic and you will not be able to do that. You have to use kind of stochastic constraints because you will never be able to achieve something. So you have again the scaling in N, right? So basically we are again working with proportions. This is just to be able to work with convergence. And then you have the decision makers that connect the task volume. That's the problem. And again, we want to maximize the total sum of the impact. So let's have a small discussion with respect to the constraints. What we assume is that the constraints are positive and the alpha are negative. Because in the resource allocation, actually, usually it is the case when you have a routing matrix, so when you have weights and so on, you don't have negative weights. So this is where it's positive. And we assume that basically there is an action which is putting D at 0. And this is actually extremely important. It's not obliged to have it, but it's important because it's like you do nothing, so it's not consuming resources, and therefore you always have a way of satisfying your constraints. Because the problem is, in some cases, you need to ensure that for every step, you have an action that is satisfying this constraint, right? Otherwise, you don't have it. So this is just a simple way of doing it. As long as you have feasibility, you have fine. Otherwise, it means that you have to avoid this set, right? If there is some state where you don't want to go, then it's again making the problem much harder. Okay. So let's try to get the optimization problem, and basically it's like yesterday, but the only thing that is different is this constraint. So you can see that the problem of yesterday is less general, right? It's forecasting this one. And again, the problem of yesterday was hard. You can guess that this one is just much harder. Again, same trick as before, and during yeah. Okay, it's a good question. Your MDPs as such are not coupled, right? The transitions are evolving independent. What is coupling them is the action. It's my policy that is coupling. Why am I obliged to couple them? Because of these constraints. If these constraints were in the payer function, right, everything would be decoupled. But because we are obliged in the action to make sure that this budget constraint is satisfied in some sense, I'm coupling everything. But through the control, it will be strongly coupled in some sense if the transition of one arm is depending on the other arm. So again, and this tomorrow also you will see me doing the same.
Excuse me, sir.
Yeah.
So can you please tell what is that variable L?
There is multiple constraints.
L.
Yeah, L. This one, right?
Yeah.
There is multiple constraints. It's a number of constraints, right? It's in there. So in our previous example, we had one constraint, right? But in the examples that I described today, we have two constraints. And you can imagine that L of them, right?
So, for example, Nilesh, if you have you only allow one arrival, right? You're going to look at all the states and pick one. So now your decision is based on the entire state at that time. That's how it gets coupled. Even though their evolution sort of don't depend, their services are independent and arrival times are independent, but because you take a decision based on everyone, so it becomes coupled.
Yeah, perhaps, when you do scheduling on parallel queues, so the evolution of the queues are in some sense independent, right? But depending, for example, the moment you use a policy like join the shortest queue, you couple everything just by the action. Because join the shortest queue is making your action depending on the state of every queue, right? Because you have to find the shortest queue. So this is also weakly coupled and weakly. So again, we do the relaxation, we take everything in expectation, right? So basically, the trick of what I'm presenting yesterday, today, and tomorrow is when you have a random variable, take it as an expectation, always, because usually it's simplifying everything. And then again, we will have an LP to solve, but with a more complex constraint. Before it was just a summation of S of Y(S1). Now you have this constraint to satisfy with all N. So I forget the all N.
Here also we are assuming only two actions. Here also we are assuming only two actions.
No.
Then what is YS0, YS?
Because I've just taken the previous linear program and I've just copy and paste.
It's a typo.
It's a typo. So there is a sum there. There is
Sum
a
of all that.
So Okay. So let's denote Y star the solution of this LP problem and N star the solution. Actually, well, with the corrective vector. The question is now how to construct again an LP policy. And basically, you could use the projection algorithm, but we'll see another one. And I think I will stop for now. And tomorrow morning, I will show you what is a LP admissible policy, a new type of policy. Okay.